I finally understood why I had timing differences when running the sweeping servo homework assignment. I used pull no block, whereas the solution Paul showed in his lesson 99 video did the pull outside of the state machine in Python code. When I ran those, the sweeps went at different rates, and I wanted to understand why. So in my Thonny window, I have two programs. I have a pull no block and a Python pull program. The pull no block is my solution. The Python pull is essentially what Paul showed in lesson 99 with some added code in it. On the left you see my servo. I've got a little presentation that we're going to be going along with. The pull no block I've earlier discovered takes 7.24 seconds to do a total sweep, 0 to 180 and then 180 to 0. The pull in Python code only took 3.1 seconds to do that same sweep. Didn't understand why they weren't the same. Wanted to understand it. So I went back to the source code and added some timing to help understand it. Just for completeness, this is my environment. The PC I'm using is a Raspberry Pi 4B, 8 gigabytes of memory, using operating system Bookworm 64-bit. I'm using a Raspberry Pi Pico. The MicroPython is version 1.24.1, and I have a bench power supply that powers the servo. I'll hide this. Servo, Pico, bench power supply. Take a look at the pull no block code. It hasn't changed except for the timing. You just slowly scroll through it. You've seen it before. Now, I only added the timing in this first for loop. I take a timestamp at the beginning of one of the iterations of this loop, and then I take a timestamp before and after the put, and I take I save the put time, which is between U0 and U1, and I save the loop time, which is between V0 and V1, U1, to be looked at later. I did not do that in the second loop. We're only going to go through one iteration, so one sweep, and after it's done, it does this printing, and I gather that data. Before I run it, let's look at the sweeping servo Python pull program. Looks just the same as I had it before. I commented out the pull no block. That pull is now out in Python code. I left side set. Paul didn't use side set, but I did. Code didn't change here at all. We prepped the state machine, but we did not do that final copying of the OSR to X. I've added another list, not an array, a list, to gather the pull times, since they're done here in Python code. And again, I only did the timing in the first loop from 0 to 180. I still have the beginning time to calculate one loop iteration, a time to count timestamps to count the put, another timestamp so I can count the pull, and then I save those 3 put times, pull times, and loop times. And then down here, print those values. So we're going to first look at this one. Watch the servo. And that was about 7 1/4 seconds. So now let's run the other one. Watch the servo. And that was right at 3 seconds. Now let's head to the presentation. And I'm going to go full screen with it here. These are the timings for the pull no block. Now if you saw that little quick look at the code, I saved the degree. I didn't save the degree, but I saved the put and the loop values in microseconds. Well, actually in seconds. And these are the first few values and the very last values. The degrees went from 0 to 180. Now you'll notice that the puts are occurring in roughly 46 microseconds until we hit the put for degree 4. And an entire loop iteration is roughly 90 microseconds, that all of a sudden switches to this 19 milliseconds, and this just stays for the rest of the run. Now first this is, what happened? Let's go to the next slide, and remember there's 4 of those that were okay, and it went bad on the 5th one, and that's a big clue. So here's what happened. PIO is running its 20 millisecond loop with the pulse width value for 0 degrees when we get going. The first 4 puts take, in that loop iteration, roughly 360 microseconds, 90 for each one. At that point, the TX FIFO is full, so when you try to do that 5th put, it stalls because there's nowhere for it to go, because the PIO program hasn't finished its loop to go back to do the pull no block. So there's a stall time of almost 20 milliseconds, 19.640 milliseconds. So when it finally pull no block occurs and takes it, there's a slot open and the 5th one will go on. But again, the TX FIFO is full, so the 6th one is going to stall, and this will continue until we're done. Everything, let me just look back quickly here. The first 4 puts, 1, 2, 3, 4, FIFO's full. You get a stall until we can get the 5th one. When the 5th one finally goes on, it's full again, so there's stalls for the rest of the run. That finishes that slide. So here's the analysis here. All 362 OSR values were used. 0 to 180, that's 181. 80 to 0, that's another 181. From the very first slide, I said the whole sweep took 7.24 seconds. So it looks like 20 milliseconds is just about right for each degree. So each OSR value is 20 milliseconds as expected. Now let's go on to the other one. It wrote out 3 values in addition to degree: the put time, the pull time, and the loop time. Now notice the loop time is 8.6 roughly milliseconds. Put times are in line with what we saw before. And that's true all the way down the line. So here's what happened in this one. 20 millisecond loops running on PIO with 0 degrees. The first put-pull for 0 degrees took 8.6 milliseconds, got put in the OSR. Remember, the PIO program is in its loop. It hadn't reached 20 milliseconds yet. But there's 11 milliseconds left in its loop. Second put-pull for 1 degree takes 8.6 milliseconds. OSR just got updated. PIO program doesn't know that. But there's 2.8 milliseconds left on its loop. The third one, the put-pull and the collides with the PIO loops move from OSR to X, but since the put-pull started first, it'll win. So the value for degree 2 will get into the OSR, and that'll be used for the next 20 millisecond loop. And this continues for the remainder. 2 skipped, so every third value will be used. So until we reach the last one, which is 179. That ends the sweep. Now going back, the 180 at the end of the first for loop and the 180 at the beginning of the second for loop will be skipped. Those OSR values will be skipped. And then we'll drop our way down in threes until we reach 2 degrees. 1 and 0 won't be used. That ends the second loop. 1's ignored. 0 will end up being used since there's no more put-pulls. So here's a summary. Roughly 362 divided by 3. So roughly a third of the OSR values are used. The other 2/3, nope, not used. From the first slide, the sweep took 3.1 seconds. Doing that same calculation, we see that each OSR value that did get used roughly 20 milliseconds, as we would expect. And to me, that explains the shorter time, the skipping of 2/3 of the OSR values. Summary. PIO pull no block works just fine. I was surprised by seeing the saturation of the TX5.0, but really shouldn't have been, because the MicroPython code runs a lot faster. But we lucked out. The saturation acts as a governor for the sweep to keep it from missing one of the degrees. The Python pull behavior is now explained. Since it skips 2/3 of the values, it goes a lot faster because it misses 2/3 of them. You really need a governor to sync the put-pull pair with the PIO code. Now, one perplexing point is that what was shown in the Pico Lesson 99 solution is essentially the Python pull program here. If you rewatch the video, you'll notice that its sweep time appears to be almost the same as the pull no block time we saw here. Do not know why it didn't match the Python pull time we saw here. Anyway, out of time. Thanks for watching.